Hello everybody, welcome to E-Pathshala. I am Tapabroto Sarkar from Indian Institute of Science Education and Research, Kolkata. I am working there as an assistant professor. Today I will talk about decay schemes of potassium-argon, uranium-lead, rubidium-strontium and samarium-neodymium systems, the petrogenetic implications of rubidium-strontium and samarium-neodymium system, and later the radiometric dating of single minerals and whole rocks. This entire module will be completed in 2 lectures. I am starting the first lecture now. In the first lecture, actually I will start with the decay of radioactive parents to stable daughter. I will derive the equation and then describe the concept of half-life, and later I will move on to the rubidium-strontium system, the potassium-argon system, the samarium-neodymium system and the uranium-lead-thorium system. I will briefly describe all these systems and developed each specific equation which is required for petrogenetic implications and radiometric dating, and the rest I will cover in the second lecture. So, the first thing which I would like to revise before going into the details of the chapter or the module is that the term isotope. So, the term isotope actually means that one of the 2 or more atoms that have the same atomic number, that is the same number of protons, but the different number of neutrons. For example, carbon 12 carbon, 13 carbon and 14 carbon. The origin of the term isotope comes from the Greek word which are 2 in parts, which is isos meaning equal and topos meaning the same place, because all isotopes occupy the same place in the periodic table. So, the isotopes can be divided into 2 parts, which is a stable isotope which does not decay and remains indefinitely in the same way. For example, the isotopes of carbon, hydrogen and oxygen. And another one is radioactive isotopes, which constantly breaks down or decays into some stable elements or stable isotopes. The radioactive isotopes, the ones which is the original radioactive isotope before decay, is called the parent isotope, and the resulting isotope which forms after the decay of the radioactive isotope is called the daughter. Next, I will describe the decay of the radioactive parent to the stable daughter. The theory of radioactivity states that the rate of decay of an unstable parent atom in a sample at any time t is proportional to the number of parent atoms existing at that time, which is n. And if we write it mathematically, it turns down to dn by dt is proportional to n. The negative sign in front is because the n is constantly decreasing with t. Now, lambda is a proportionality constant which can be written, now the equation can be written as minus dn by dt equals lambda n, where n is the number of parent atoms, t equals time and lambda is the proportionality constant called the decay constant, and dn by dt is the change in n or the number of parent atoms with respect to time t or the rate of decay at any particular time. Now, if we rearrange the equations minus dn by dt equals lambda n, we can write minus dn by n equals lambda dt. Now, if we integrate this equation on both sides, then the ultimate equation is minus ln natural log of n equals lambda t plus c, where c is a constant. At the time when t equals 0, then according to the equation n equals n0, then the c, the constant, becomes minus natural log of n0, where n0 is the original number of atoms of the radioactive nuclide. Now, in the in the last equation, if we replace the value of the C, that is the value of the constant, then we get minus natural log of n equals lambda t minus natural log of n 0. Now, by rearranging the equations, we can write minus natural log of n by n 0 equals minus lambda t, which can be rewritten into n by n 0 equals e to the power minus lambda t. So, this is n equals n 0 into e to the power minus lambda t is the fundamental equation which is used in the radioactive decay studies, and we shall see how this fundamental equation varies with the different isotopic systems, which will be discussed in detail in the following slides. So, the next what I will discuss is the concept of half-life. What we know is that the rate of decay is proportional to the number of parent atoms remaining in the sample at any time. Therefore, what we can say is that the constant proportion of the remaining parent atoms decay in a fixed time period. Therefore, we can say that the half of the unstable atoms in a sample thus decay in a specific time interval, which is some function of the decay constant, that is lambda. So, that is the definition of the half-life, that is the time required for half of the unstable atoms to decay into daughter atoms. For example, if the initial number of parent atoms is n 0, then after one half-life the number of parent atoms will be half n 0, and after two half-lives the number of parent atoms will be 1/4 n 0, and it will continue so on. Now, if we want to put this in a mathematical format, we can substitute the values of n and n 0 in the fundamental equation. So, the n becomes half of n 0 after one half-life, then n 0 e to the power lambda t. In place of t, we can put t half, which is the notation of half-life. Then if we calculate this equation, it comes to natural log of half equals minus lambda t half, where it comes down to t half equals natural log of 2 by lambda, which is 0.693 of lambda. This indicates that the t half or the half-life of a radioactive atom is inversely proportional to the decay constant, which means that higher the lambda or the decay constant, lower is the t half or the half-life of the atom. So, this is the graphical explanation or the graphical figure which shows a graph with half-life on the x axis and the relative number of atoms and the y axis. What you can see out here is that the parent atom is uranium-238 and the daughter atoms are lead-206. At the beginning of time, when t equals 0, there is 100% or let us say 100 uranium-238, which are the parent atoms, and 0 lead-206, which is the daughter atoms. So, after one half-life, the number of the parent atoms decreases to 1/2, that is 50, while the number of the daughter atoms increases by 50, which is equal to the number of parent atoms that has decreased. And after two half-lives, the parent becomes 1/4, that is 25, while the daughter becomes 75, and it follows in this pattern. So, what we get is that the parent atoms decreases exponentially for each half-life. Now, I move on to the principles of radiometric dating. So, first what we need to do is we need to derive the basic equation from the equation of radioactive decay, which can be used for radioactive dating. What we know so far is that n equals n 0 into e to the power minus lambda t is the basic equation for radioactive decay. But now the question is how to measure the time t from this equation. Technically, if we know n, which is the number of atoms present, n0, which is the number of atoms present in the beginning, and lambda, which is the decay constant, we can ideally solve for the time t, where t equals the number of years that have passed since the decay process began. But the problem is how to measure n0 for a modern sample. How do we know the number of atoms which was present in the beginning for a sample which we see today? It is practically impossible. We can, however, determine n0 from the number of daughter isotopes which is produced in the time t. This is the other way of determining the number of parent atoms which was present from the initial time. Let d star be the number of radiogenic daughter which has been produced from n0, which is the number of parent atoms at any time t, and n be the number of the remaining parent atoms at that time. Then we can write that d star, the number of radiogenic daughter, is definitely equals to the number of atoms present in the beginning minus the number of remaining parent atoms at time t. So, d star equals n0 minus n. Now, we can of course substitute n0 by n equals e to the power lambda t, which we derived earlier. Then we can get d star equals n into e to the power lambda t minus n, and which is equals to n into e to the power lambda t minus 1. Now, technically from this equation we can solve the value of t if we know the d star and n. D star is the number of radiogenic daughter. But the problem is the total number of daughter isotopes may not be equal to the number of radiogenic daughter from the radioactive parent. Why? Because at any point in the sample, the daughter isotopes might already be present from the beginning. Therefore, the total number of daughter isotopes denoted by D would be equal to the original number of daughter isotopes, that is D0, plus the radiogenic daughter, that is D star. So, we can write in the form T equals D0 plus D star. Now, if we replace the value of the D star in the previous equation, we get another equation D equals D0 plus n into e to the power lambda t minus 1. And this is the basic equation which is used for age determination of rocks and minerals based on the decay of active parents. And with this development of the basic equation, I move on to the fundamental systems or the isotopic systems, and I would start with the Rubidium-Strontium RBSR system, which is one of the most common isotopic systems used by petrologists. So, basically rubidium-87 or 87 rubidium decays to 87 strontium plus a beta particle, which has a T half of or half life of 4.88 billion years. The important characteristic of the system is that rubidium behaves like potassium. So, it concentrates in micas, amphiboles and K feldspar, and strontium behaves like calcium. So, it concentrates mostly in plagioclase and apatite. 86 strontium is a stable isotope and is not created by the breakdown of any other element. Now, we have already developed the basic equation. Now, if we write this equation will take the form for this system, and we can write it in the form 87 strontium equals 87 strontium 0 plus 87 rubidium into e to the power lambda t minus 1. Now, if we divide this equation on both sides by 86 strontium, which is a stable isotope of strontium, we will get such an equation where 87 strontium by 86 strontium equals 87 strontium by 86 strontium 0 plus 87 rubidium by 86 strontium into e to the power lambda t minus 1. This is the basic equation which is required, which needs to be solved to find out the time for the rubidium-strontium system. So, here is the basic equation. How do we find the time t? we can measure 87 strontium by 86 strontium and 87 rubidium by 86 strontium readily from the rocks and the minerals. But 87 strontium 0, which is the original amount of 87 strontium which was present when the decay started, it is very difficult to determine directly from the sample. So, the question is, how do we find this value? So, this initial isotope ratio 87 strontium by 86 strontium 0 in this equation as well as the time t need to be derived from graphical analysis of a suite of rock samples. How is that done? I will describe this immediately. So, the equation which I am talking about so far is in the form of a straight line, which is in the form of y equals c plus mx. So, if we have a plot which plots 87 strontium by 86 strontium versus 87 rubidium by 86 strontium, which is the y versus x axis, the plot of a straight line m, the slope of the straight line m will be equal to e to the power lambda t minus 1 and the y intercept will be 87 strontium by 86 strontium 0. Now, I would explain how we can find out the initial ratio, which is the 87 strontium by 86 strontium 0 from the graphical analysis. Let A, B, C these points be 3 samples with same initial 87 strontium by 86 strontium value. For example, different minerals in the same rock that crystallize together. So, when time equals 0, t equals 0 at the time of crystallization, all the minerals in the given rock will have the same 87 strontium by 86 strontium value, because the minerals cannot fractionate or discriminate between these relatively heavy isotopes of strontium. So, at time t 1, which is some time later, a fraction of 87 strontium atoms in each of these minerals A, B, C have decayed to 87 strontium. So, definitely the 87 strontium by 86 strontium ratio will increase for each sample, and which is denoted by the points A 1, B 1 and C 1. The amount of 87 strontium by 86 strontium will depend of course on the initial value of rubidium, 87 rubidium by 86 strontium ratio. So, the position of each mineral in the rocks shifts along a line to the next set of points, which is A 1, B 1 and C 1, and after a certain time, which is time t 2, it will move again to another points, which is A 2, B 2 and C 2. The slope of the resulting straight line will be e to the power lambda t minus 1. It will all these points will lie on a straight line, and the intercept on the y axis is the initial strontium ratio, which is 87 strontium by 86 strontium 0. The slope will increase with time, while the y intercept will always remain constant. So, when we have an unknown sample, we will get only such a line where all the samples will fall on a single line, and the line will cut on the y axis, and the y intercept will basically be 87 strontium by 86 strontium initial. So, next we move on to the potassium-argon system, and we develop the equations in the similar way as the rubidium-strontium system. Here the potassium-40, which is a radiogenic variety of the potassium element, undergoes a branching decay to produce 2 different daughter products. One is potassium-40-19 plus a beta particles gives argon-40. Another is potassium-40 decays to calcium-40 plus a beta particle. Now, each branch of the decay scheme has its own separate decay constant. Then the total decay constant lambda is therefore the sum of these. So, lambda equals lambda of C A, which is the decay constant of this branch, and lambda A R, which is the decay constant of the first branch. So, the proportion of potassium 40 atoms that decay to potassium argon 40 is given by the ratio of the decay constant as it has been noted out here. So, similarly for the potassium argon system, the basic equation which we derived can take the form of potassium 40 argon equals 40 argon 0 plus lambda of argon divided by lambda into 40 potassium into e to the power lambda t minus 1. Now, in the similar way, if we divide this equation by a stable isotope of argon, which is 38 argon, we obtain the general equation which is used for age dating, which takes the form what is written on the slide. So, and here is a simple thing about the potassium argon system is that argon is a noble gas which escapes during a geological event. So, 40 argon 0, which is the initial argon present, will be always 0. So, subsequently 40 argon is only produced by the decay of potassium and is trapped in the solidified mineral or rock. So, the best part of the technique is that a single rock sample provides a value for 40 argon and 40 potassium, and thus we can calculate a value for the age. We do not have to do a graphical analysis to find the value of t or the time. So, next I move on to the next isotopic system, which is the Samarium-Neodymium system or the SN-ND system. So, in this system 147 samarium decays to 143 neodymium plus an alpha particle. And for the Samarium-Neodymium system, the basic equation will take the form 143 neodymium equals 143 Nd0 neodymium 0 plus 147 samarium into e to the power lambda t minus 1. Now, in the similar way, if we divide both sides by a stable isotope of neodymium, which is 144 Nd, we obtain the general equation used for age dating, which is 143 Nd by 144 Nd equals 143 by 144 Nd0 or initial plus 147 samarium by 144 neodymium into e to the power lambda t minus 1. The system is very similar to the Rubidium-Strontium system. For example, sum of 143 Nd is already present in the rocks before the radiogenic 143 Nd is added. Therefore, we need to calculate or need to find out 143 by 144 Nd initial. The initial ratio 143 by 144 Nd in this equation as well as the time t need to be again derived from the graphical analysis, which is the isochron method from a suite of rock samples, very similar to that showed for the Rubidium-Strontium system. So, I will move on to the last system which I will discuss in this lecture is the Uranium-Thorium-Lead system. So, this is a set of 3 independent decay schemes with 3 radioactive isotopes, which is 238 uranium, 235 uranium and 232 thorium, plus 3 radiogenic lead isotopes which decays from these radioactive isotopes, which is 206 lead, 207 lead and 208 lead. We can here we can see is that 238 uranium decays to 206 lead, 235 uranium decays to 207 lead and 232 thorium decays to 208 lead. What you can see is that the half life is very different for 3 different decay schemes, and we ultimately have 3 different isotopes of lead. So, from these 3 independent decay schemes, very similarly we can write 3 equations with reference to a non-radiogenic 204 lead, and these equations can be used for age determination. So, the first equation would be 206 by 20 lead equals 206 by 204 lead initial plus 238 uranium plus 204 lead into e to the power lambda 1 T minus 1. Here the 3 decay or the 3 decay constants are denoted by lambda 1, lambda 2 and lambda 3 for the 3 different decay schemes. The second equation would be 207 lead by 204 lead equals 207 by 204 lead initial plus 235 uranium by 204 lead into e to the power lambda 2 T minus 1. And the for 208 lead from 232 thorium, we have a similar equation. So, ages of a mineral or a rock can be independently found from all 3 different decay schemes. Ages, the same age can be independently derived from all the 3 equations. So, each of these equations which have been developed in the last slide you have seen. So, each equation, from each equation we can find out a time which is T. In ideal situation, all this time or all these ages from these 3 equations should be equal. But the problem is, in many instances we see that the time or the ages which is found from all 3 equations are not equal, due to the diffusion of uranium, thorium and lead or the intermediate nuclides from the system which is a mineral or a rock. So, to understand where the diffusion has taken place or to solve this complicated situations, we have developed an idea of Concordia and Discordia to better understand the situation, which I will be explaining in the next slide. So, now I would develop or explain the concept of Concordia and Discordia in the uranium-thorium-lead system. For the 2 isotopic systems of uranium, which is 238 and 235 uranium, the amount of radiogenic lead, which is Pb star at any time must be, as we have discussed earlier, 206 lead star equals 238 uranium into e to the power lambda 1 T minus 1, or 206 lead, we can rewrite this in the form 206 lead star by 238 uranium equals e to the power lambda 1 T minus 1. It comes from the previous equation that I already discussed. Similarly, for uranium 235, we can write 207 lead star by 235 uranium equals e to the power lambda 2 T minus 1. Now, if a uranium bearing mineral behaves as a closed system, then we should get concordant ages, that is the same value of T from these 2 equations. Conversely, what we can say is that at any given time T, that is if we fix the value of the T, then 206 lead star by 238 uranium and 207 lead star by 235 uranium will have compatible values, because the value of lambda 1 and lambda 2 is a constant. So, what has been done is that in a 207 lead star by 235 uranium versus 206 lead star divided by 235 uranium plot, the loci of all the concordant points in a uranium lead system should represent a curved line which is known as Concordia. So, which is shown in the next slide. For example, so this is a Concordia diagram where the curved line is basically the loci of all the concordant points in the uranium lead system. So, as you can see in this diagram, we have a curved line, and as uranium 235 decays much faster than uranium 238, naturally 207 lead by uranium 235 has a much higher value than 206 lead by 238, and that is why we get a curved line which is concave downwards. So, now suppose 2.5 billion years after the evolution, all the points or the concordant points should lie on the Concordia curve. But if there is an geological event where there is a loss of lead, then these concordant points will move along a straight line straight towards the origin, and this line will define a line which is called a discordia. If all the lead is lost, then definitely the points will come to the origin. So, let us assume that we have 4 different samples which has suffered loss of lead at after 2.5 billion years of evolution. Then the one which has completely lost the lead will come down to the 0 and will follow a straight line, because during the lead loss both 206 lead and 207 lead will be lost at the same proportions. But the sample which has not lost any lead will still continue to stay on the Concordia diagram, and the ones which has lost part of the lead will fall on this discordia. And let us say 1 billion years after this event, where there is a partial lead loss, partial to complete lead loss, then all these discordant points will still remain on the straight line, which is the discordia, and this discordant line will cut the Concordia at 2 places. One is called the upper intercept and what is called the lower intercept, and this upper and lower intercept has also geological significance, as we can find out the age of the another geological event where partial lead loss has taken place. So, what we have discussed today is the different types of isotopes. One is stable isotope and radioactive isotope, and the decay of radioactive isotope to a stable parent, which is dependent on time. We have used this technique, the dependence on the time, to find out, or the technique to find out the ages of the different samples which are rocks and minerals. Then we moved into details of 4 isotopic systems used for dating of minerals and rocks, which is the Rubidium-Strontium system, the Potassium-Argon system, the Samarium-Neodymium system, and the Uranium-Thorium-Lead system. For all these systems, we derived the equation used for radioactive dating and the specific techniques which can be used to date different rocks and minerals. Each system has its own characteristics and own slightly different ways of finding out the ages, and in the next lecture we will discuss about the petrogenetic importance of these systems and the techniques of how we can exactly determine the ages, geological ages of minerals and rocks, and what are the meaning of these ages. So, thank you very much.